In this video, we are going to evaluate some definite integrals using Cauchy residue theorem in complex analysis. We are going to evaluate type 2 integrals. Type 2 integrals are of the form integral minus infinity to plus infinity f of x dx or integral 0 to infinity f of x dx, where f of x is equal to g of x by h of x, where g of x and h of x both are polynomial in terms of x. And this is the equation what we are going to use for evaluating the integral over c f of z dz. This is type 1. Already I have posted a video for type 1 integrals. Kindly watch that video before you are going to work out type 2 integrals. So using type 1 only, we have to integrate, we have to find the pole, we have to find the residue, and we have to use Cauchy residue theorem, and we have to find the integral. Okay, so after that, using this equation, we have to convert the given we have to convert the answer what we are getting from type 1 integral to this type. Okay, so integral over c f of z dz, that is the curve which we are going to use for type 1, is equal to minus r to plus r f of x dx. Minus r to plus r means it is a straight line. Integral over c1 is a semicircle. C1 is a semicircle combining with this minus r to plus r. So C1 f of z dz. So using this only, final answer we are going to convert to the given problem. So please go and watch type 1 video. After that you watch this one. This is the first problem what we are going to see now. Using the method of contour integration, evaluate integral minus infinity to plus infinity x squared by x squared plus 1 into x squared plus 4 dx. So we have to, first step is you take the given term as f of x, and from that you convert x to z. So find f of z. F of z is equal to, convert every x to z. So z squared by z squared plus 1 into z squared plus 4. And as usual what we did for type 1, we have to do. So type 1, first we have to find the pole, and if the pole lying inside the circle, we have to find the residue, and Cauchy residue theorem finally we have to apply. So Cauchy residue theorem is equal to 2 pi into sum of the poles. Integral over c f of z dz is equal to 2 pi into sum of the residues. So for that, first I am going to find the pole. So equating the denominator equal to 0 means this term, either this term or equal to 0 or this term equal to 0. So if it is equal to 0 means z square plus 1 equal to 0. That implies z square is equal to minus 1. Minus 1 can be written as I squared. So z squared is equal to I squared. Therefore z is equal to plus or minus I. So two poles we got. And when we take the second term equal to 0, z square plus 4 equal to 0 means z squared equal to minus 4. Minus 4 means minus 1 can be written as I squared. 4 can be written as 2 squared. So I squared, 2 squared. So we can rewrite this as 2i the whole square. So z squared is equal to 2i the whole square. Taking square root on both sides, z is equal to plus or minus 2i. So plus 2i minus 2i. So combining all the roots, I minus I plus 2i minus 2i. For I the point is 0, 1. For minus I the point is 0, minus 1. For 2i the point is 0, 2. For minus 2i the point is 0, minus 2. Okay. So first you have to confirm which point lying inside the circle. This is our circle. This only we are taking. So which points lying, only we have to take the positive axis, right? Positive x, positive and I'm sorry, not positive axis. We have to take the first two quadrants. First two quadrants means x y positive, x negative, y positive. Only those points we have to consider. So this point lying in the first quadrant. So where it lies? 0, 1. And 0, minus 1. 0, minus 1, where it lies? This negative y-axis. It is not in our curve, right? So we are considering C1 the semicircle on the straight line minus r to plus r. So this one does not lies. And 0, 2, where it lies? 0, 2 means this point, 0, 2. So this one lies. 0, minus 2 means in the negative axis of y. So this one is not lying inside our curve. So only 2 points lying inside, I, I comma plus 2i plus I comma plus 2i. For those 2 points only, we have to find the residue. What is our f of z? F of z is equal to z squared by z squared plus 1 into z squared plus 4. So we can take this as h of z by k of z. For the pole, first we are going to take I. Okay, so what is the formula for finding the residue? Residue of f of z at the pole, not z, at the pole, this is pole. At the pole I is equal to h of I by k dash of I. Okay, so what is h of I? We have to calculate both the terms. First, k of z. K of z is equal to z squared plus 1 into z squared plus 4. We have to multiply, we have to expand and simplify. So after expansion, we are getting z power 4 plus 5 z squared plus 4. If you do the differentiation with these two factors, you have to use UV method. So keeping one term as it is, differentiating the second, plus keeping this term as it is, differentiating the first term. Okay, so for avoiding that, first you have to multiply the terms, we have to expand and arrange in order z power 4 z squared constant term. After that, I am going to differentiate. When I differentiate this, this is 4 z cube plus 5 into 2, 10 z plus 0. So in this place, I am going to substitute z equal to I. So 4 into I cube plus 10 into I. I cube is already we have used this. I cube is equal to minus I. I cube can be written as I squared into I. I squared value is minus 1 into I, which is equal to minus I. Right. So this can be replaced as minus 4I plus 10I. So when we add, we are getting 6I. So k dash of I equal to 6I. We have to find what is h of I. What is h of z? It is z squared. I'm sorry, it is I squared. So I squared is minus 1. So when we replace here, it is minus 1 by 6I. Already I told you, when I come in the denominator, we have to change that as minus I. So this can be simplified as minus 1 into minus I. This is minus I by 6. Minus into minus plus. So plus I by 6. This is the residue for the pole I. The next one is, I'll write the answer here. Residue of f of z at the pole I is equal to I by 6. Now we are going to find for the pole, what is the pole? Second pole, 2I. We are going to find the residue of f of z at the pole 2I, which is equal to h of 2I by k dash of 2I. h of 2I means z squared. H of z is z squared. So 2I the whole squared. 2 2s are 4. I squared is minus 1. So it is minus 4. The numerator is minus 4. Then k dash of 2I is equal to, k dash already we calculated, no, 4 z cube. So 4 into 2I the whole cube plus 10z plus 10 into z is 2I. 2 cube I cube. 2 cube is 8. 8 4s are 32. I cube is minus I. So minus I plus 20I. So it is minus 12I. So minus 12I. Minus minus we can cancel. This also we can cancel. 3. I, when we take to the numerator, it is minus I. So minus I by 3. Therefore, residue of f of z at the pole 2I is equal to minus I by 3. Now, we are going to use Cauchy residue theorem for finding the integral. Integral over C f of z dz is equal to 2 pi I into sum of the residues. What are the residues we calculated? First residue is I by 6 and the second one we got as minus I by 3. So which is equal to 2 pi I, taking the LCM 6, I minus 2I, which is equal to 2 pi I, this is minus I by 6, which is equal to cancellation of these two. My minus we can take to the front, pi I squared by 3. Minus, I squared is minus 1. Minus 1 into minus plus, so pi by 3. Therefore, integral over C, f of z dz is equal to pi by 3. So up to this we are following type 2 integration, so that is very important. And after that we are going to use this answer in the equation, first equation what we took. No, 1 minute. This equation I said no, here only we are going to apply. Okay, so what is the equation we have? Integral over C, f of z dz is equal to integral minus r to plus r, f of x dx plus integral over c1 f of z dz. This answer only now we got. What is this answer we got? Pi by 3. So instead of this we can take pi by 3 is equal to the same term. Taking limit r tends to 0. When I take r tends to 0, what I am getting is pi by 3 is equal, r tends to infinity, because the integration is minus infinity to plus infinity. No, r tends to infinity. We have minus infinity to plus infinity, f of x dx plus this term will become 0. So when we take r tends to infinity, the whole integral over c1 f of z dz will tends to 0. So this is the answer. What is the answer finally we are getting? Pi by 3. Integral minus infinity to plus infinity f of x dx is equal to pi by 3. So in this problem what we got? No, the answer for this problem is pi by 3. Is it clear? Thank you.